Hello friends, so today we are going to solve 4 questions, and these 4 questions are from electrostatics. Okay. First question. It states that two positive ions and one negative ion are fixed at vertices of an equilateral triangle. Where can a fourth ion be placed along the symmetry axis of the setup so that force on it will be 0? Is there more than one such place? This is just a basic question, and it is more or less, we can say, somewhat theoretical also as compared to the analytical analysis in this. So we can just draw an approximate figure for that, and we are given that we are having a triangle, equilateral triangle, and in this equilateral triangle we are having two positive. So let us suppose this is one positive and this is the second positive, and the third one is the negative on the topmost vertex. Okay. And let us you can say define the axis here. So the symmetric axis, about, let us suppose this is x-axis and this is our y-axis, and we assume that this equilateral triangle is having a side length of a. Therefore on the left side we are going to have the coordinate of -2 by a comma 0, and the right side we are going to have a coordinate of +2 a by 2 and 0, and this is our origin, that is 0 comma 0, and the negative will be our height of this equilateral triangle. So this will be coming as 0 square root of 3 2 times a. So these are the respective coordinates of each vertex. And so we are interested in this, you can say, now from the figure we can clearly see that the y-axis, which is our also symmetric axis, okay. So let us write it out, that we considered our y-axis, and this y-axis is also our symmetric axis, and to the left and right of the symmetric axis we have positive and positive charge. Okay. And we are said that we are going to place a fourth ion on this symmetric axis. It means the fourth ion will be placed on this y-axis. Okay, so its coordinate will be always 0 comma y. Okay, and this y can be negative as well as positive. We can just deliberate that on later on. So here we can clearly see that on this our, with respect to the y-axis, let us call this as a, and this is our b, and this is c. So with respect to this y-axis, our charge at a and charge at b are symmetric. Okay, so it means the horizontal component of force, that will be, they will be you can say applying on the test charge, okay, that we placed on y-axis, will be equal to, they are going to basically cancel out. Okay, so it means if we place a test charge somewhere here, okay, so the force, let us suppose there is a repulsive force in this direction, and because of this there is a repulsive force in this direction. So we can divide these two forces into the coordinates. Okay. And So if we divide them horizontal and vertical coordinate, so this will be for the first part and this for the second part. Therefore, from clearly here we see that our horizontal component are going to cancel out. Okay. Anywhere we keep the test charge on this y-axis, this condition will be always true. Okay. Therefore, we can say that because of the symmetry, the horizontal component of charges at A and B, charges at A and B cancels, and this will be true for every situation whenever the charge will be on this symmetric axis. Okay, because the distance between the test charge will be same. Okay. So this is the first condition, and if the horizontal component are balanced out or cancel, the only component that will be left will be our vertical component, that is our y direction. So you can say only our vertical component, that is our y direction, vertical component force survives. So only the vertical component will be left. Now we come to the, you can say, because in terms of our this balance out, one, whether there is electric field or whether there is a force, one, or whether we are finding out the energy, one critical component that is part of the calculation is the distance. Okay. So let's find out what will be the distance of each point charge. Therefore, we can say that distance, and first of all we are going to find out distance to each positive charge, each positive charge, and let us call this as our R positive, and this R positive will be our y component and plus a by 2 and its whole square and its square root, because we know in the question it is given that this test ion will be always placed on the symmetric axis, so that will be a y axis. Okay, so in general we take any point whose coordinate is y, so therefore this distance is our a by 2, and like we said we have taken this as y, so the distance between the charge and this test ion will be equal to, because this is a right angle triangle, so simply it will be y square plus a by 2 square. Now we come to the second charge, that is distance to the negative charge, to negative charge, and let us call this as R negative, and this R negative will be equal to our y minus and square root of 3 by 2, and we are taking this as modulus because this point can lie anywhere on this y axis. Okay, so we are only interested in the magnitude, so that's why we have taken this as a modulus. Okay. So from here we can see that these two distances are also not equal. Okay. Therefore we cannot solve it and combine to a single radius. Okay, so we have to take the force expression for our positive charge as well as a force expression for the negative charge in the different. Okay, they have to treat it separately because if the distance is entirely different. And like we said that because of the symmetry, the horizontal component of the force is going to cancel out with respect to both the positive ions. Okay. And this symmetry is only with respect to left and right. Okay. So you can say we have only our left-right symmetry. So because this left-right symmetry, the forces, horizontal component of forces are going to balance out, only the vertical component, or we can say with respect to y, will be left. And there is no symmetry, up and down symmetry. You can say no up-down symmetry. So basically up-down symmetry means like we have a negative charge at C, so correspondingly there is no negative charge that is present here. Okay, so that's why it doesn't have any up-down symmetry. And so it means that for specifically for this up-down symmetry, we can clearly see that the y greater than 0 is not same as y less than 0. These are entirely two different things. Therefore, from here we can say that y greater than 0 means a positive and y less than 0 is our negative. They are not same. Okay, because there is no up-down symmetry. Okay. And so now we have to find out, because one thing is very sure that one second. Yeah, so we have to find out that the force will be 0, so we can approximate it, and whether there will be more than one such situation or not. Okay, so these are the two parts of it. So in the first part, we clearly understood that because of this there is no up-down symmetry, and that results that our this y greater than 0 and y less than 0 are not same. Okay, so this is the basic, you can say, conclusion we can draw from here. And from here we can also draw one important conclusion, and that conclusion states that our okay, so let's try to find out where this point is going to lie. So let us consider two conditions. First condition is that our this test ion, it is near the negative charge. We consider this test ion is near the negative charge. And because of this, we can say the attractive forces between the test ion and negative charge are going to dominate. Therefore, we can say from here that attractive force toward negative charge dominate. Okay. And this net force will be towards negative charge. Okay. And direction will be towards negative charge. And second condition which we consider, that this test ion is far above the triangle. Far above the triangle. Now we have two positive charges. Okay. So therefore we can say that because of the forces, because of these two positive charges in combination are going to dominate. From here we can just write that all three charges are far away. And secondly, we can also say that we are having two positive charges, so we can say that two positive charges together dominate as compared to one single charge, as compared to one negative charge. And there will be the force of repulsion. You can say that the repulsion points away from the triangle. Away from triangle, or we can say upward. Okay. And so it means because of the negative charge, we have a force that is towards the negative charge, and there is a force that is points towards the far away. So from here we can say that the force points downward close to the negative charge, and we can also say that the force points upward far away. So these are the two important conclusions which we draw from these two discussions or 2 points. Therefore, from here we can say that the force must pass through 0 exactly once in between them. Force must pass through 0 exactly once in between. So therefore there will be only one point, and that will be lying between these two forces. Okay. And therefore we can say so we come to our next question. And this question states that a charge q is located at the tip of a hollow cone with a surface charge density sigma. The slant height of the cone is capital L. The half angle at the vertex is theta. What can you say about the force on the charge Q to the cone? And the second part states that if the top half of the cone is removed and thrown away as in figure, what is the force on the charge Q due to remaining part of the cone? For what angle of theta this force is maximum? Okay. So here it is given to us one second. Okay, so the basic figure is given to us. So we are given a cone. At the vertex we have charge Q and total slant height is given as L. Okay. And in the first part this cone is intact. Okay, so we have to find out what will be the force on this charge Q because of the entire cone. Okay. So in the first part this is something like this. So this is the cone and we have a charge Q and slant height is our L and the half angle is given to us as a theta. Okay, so first half and sigma is given the charge density on the this is the cone. So in the first part we have to find out the force because of this entire cone at the charge Q, and second part it says that this top half of the cone is removed. Okay, only the bottom part is left, this part is left, so we are going to find out same the force at the charge Q. Okay, so this is the basic question. Okay. And so in this case let us draw the part A and part A we draw a ring and let us call this that for this ring the slant height is our L and R is radius. Therefore let us write it out. So we say that consider a ring on the cone at slant distance L. At slant distance L. Okay. So it means we can now find out write the formula for the ring radius. Therefore we can say that our ring radius, that is our R, will be equal to L sine of theta, and we can easily find out the ring area. and ring area, let us call this as our dA. Then this dA will be equal to our 2 pi r and dl, where dl is the small thickness of this ring. So this dl is a little bit its thickness, and we substitute value of this r. Therefore we get this as our 2 pi sine of theta, and we have this as L times dl. Now this on the small ring we can find out the charge also. Therefore we can say the ring charge is our, suppose, dq. Then dq will be equal to the charge density multiplied by its area. So we get this as our 2 pi sigma, and we have this as sine of theta L dl. Now we can easily find out what will be the field because of this ring charge, that is our dq at the apex, at this charge q, and let us call this as point A. So we can write that electric field at apex, that is point A. So we can write this as our dE will be equal to k times dq and divided by our L square. And we can find out its axial component. Therefore we can say that the axial component that is our dE axial, that is our parallel, will be equal to dE cos of theta. And so we substitute this our dE, so we get the axial component will be equal to, and this is k d theta, and d theta we can substitute, so we can just directly write it as 2 pi k sigma, and we have it as sine theta cos theta, and this is our L dl upon L square. Now this length and length cancels out, so we get here that our this electric field axial component will be equal to 2 pi k sigma sine theta cos theta dl upon L. And now from here one thing is very sure, because if we move this ring all along this slant height, okay, angle of theta will be same, so all the parameter will be same, only thing that is going to change is our dl upon L. Therefore from here we can say that our axial electric field is proportional to dl upon L. Okay, rest of the things we can keep as it is, okay, for a constant or calculation purpose later on. Therefore we can write that the total electric field will be our axial electric field in terms of proportionality, and we can simply integrate it dl upon L, and this integration will be from 0 to L, okay, along the slant height. And obviously the integration of this L will be natural log of our L, okay, and one of the limit is our 0. Okay. Therefore we can say that this integral diverges logarithmically. Okay. or we can say it is undefined. Therefore we can say this integral diverges logarithmically at the apex. Or physically meaning, if we try to understand what actual the meaning in terms of this, we can say the physical meaning of this particular statement, we can say that the surface charge density is infinite. And second thing, we can also say that the surface becomes arbitrarily very close to the charge. So these two important things we can draw from this conclusion. And therefore we can say that the surface charge density is finite, and we can also say that the surface becomes very close to charge. So these are the two important conclusions which we can draw from here. So it means the one important conclusion, or if we want to make a final summation of this entire discussion, we can say that this complete cone will be having a force on Q is infinite or undefined. Therefore we can say that the force on Q is infinite or undefined. So this is the first part. Second part is much more, you can say, easier, and that's why specifically for the second part was asked for, because in the first part it says that what can you say about the force on the charge at Q due to this cone. So obviously that is our undefined. So in the second part it says that the top portion of this cone is removed. So this cone is removed, but charge is already there. Okay, so we have to remember the charge is there, but the top portion of the cone is removed. Now the limit is going to vary from our 0 to L by 2. Okay. So this is the, we can say, our major difference, or sorry, not 0 to L by 2, but this will be 0, this will be L by 2, and this will be L. Therefore the small l will be lying between our capital L, and it will be greater than or equal to over L by 2. Okay, so this will be the limit of our integral, whereas in the first case it was our from 0 to capital L. So this is a major difference between the two, and because of this the entire solution of the equation is going to change. So we come to the part B, and part B, it is given that top half is removed, okay, or we can say removing top half of the cone. Top half of cone, and removing top half of the cone, you can say that the cone exists only for our L by 2 less than equal to L and less than equal to capital L. So same expression we are going to use, but now the limit will be entirely different. Therefore, you can say the axial electric field is our varying from L by 2 L, and this is our dl upon L. So we can easily solve it. This will become again natural log of L, and this is our L by 2 and L. So we get this as our natural log of L minus natural log of L by 2. Therefore, we can say that our electric field, axial electric field, will be proportional to this comes as our natural log of 2. So this is our electric field due to this. Okay. And second thing, it asks for, so now we can put this entire into this equation. Okay, so we have just for the sake of convenience we have removed it. Therefore, we can say that our electric field will be equal to 2 pi k sigma sine theta cos theta and natural log of 2. And then we can easily find out the force on this because of this electric field. Therefore, you can say that force on charge Q will be equal to over F, and this will be Q multiplied by the axial electric field, and this gives us 2 pi k q sigma sine theta cos theta natural log of 2. And then we have to find out the angle for maximum force. Angle for maximum force. And in order to solve this, we are going to combine these two along with this sine theta and cos theta. Okay. So we can simply write this as rest of terms will be same. So we can get this as sine 2 theta. Okay. So we are only interested in this term, sine of 2 theta. Okay. So from here we can write that our force theta is suppose proportional to this sine of 2 theta. And in order to maximize, we know for maximization this sine 2 theta should be equal to 1, or we can say our theta should be equal to pi by 4. Okay. So we can say our theta max will be equal to pi by 4. So this was a little bit tricky in the first part, but much more convenient in the second part. Okay. Come to the next question. And in the next question, we are given that 2 protons, 2 electrons are located at the corners of rectangle with side lengths A and B. There are 2 essentially different arrangements. Consider the work required to assemble the system, starting with the particles very far apart. Is it possible for the work to be positive for either of the arrangements? If so, how must A and B must be related? So in this case, we are given total 4 charges. 2 are positive and 2 are negative, 2 protons, 2 electrons, and they are arranged in the rectangle with the side are A and B, and it says that there are 2 different arrangements in which these 4 charged particles can be arranged. Obviously we can draw it also. And another thing it asks for that we I have to find out the work, and for work it is much more convenient to find out the total electrostatic potential energy, okay, because that work equals to total electrostatic potential energy. Okay, so we start from there. So we say that work equals total electrostatic potential energy, and we know the general formula for this potential electrostatic potential energy, and this electrostatic potential energy is suppose U, then this U is represented as the summation of our K, and this is our charge number 1 Qi, charge number 2 Qj, and the distance between the two and their summation. And we know that our K is equal to 1 upon 4 pi epsilon naught. So this is the general formula for our this charges, and in this case we are given total 4 charges. Okay, so let us first of all draw the necessary arrangement, because it says that it has 2 different arrangements. So let us call arrangement 1. And this arrangement 1, we are given a rectangle, and the arrangement 1 side is given as our length is our A, and breadth is given as B. Therefore let us assume that the first arrangement is our plus E, and this is our minus E and plus E. So this is our first arrangement where the charges are arranged, same charges are on the diagonal. And we can easily find out the distance between these two. That will be our A square plus B square and its square root. Now let's find out, because the potential energy is nothing but the combination of the charges. Okay, always there will be 2 charges for the potential energy. And so let's find out pair contribution. Okay, so the arrangement 1, we can write it like this. This will be plus E, minus E, minus E and plus E. This is our arrangement number 1. And now let's find out the pair contribution. And for pair contribution, first is our horizontal edges. And there are 2 horizontal edges. Okay, let us call this as our A, B, C and D. So 2 horizontal edges between A and B and D and C. Okay. So we have 2 horizontal edges, and distance between these 2 horizontal edges is our A. Therefore we can write this as our 2, and this will be going minus K E square upon A. Okay, so this is our horizontal edges. Then we come to our vertical edges. And vertical edge is also 2. We have vertical edge AD, and another one is our BC. So, and the distance between the 2 is our B, and this comes as minus K E square upon B. And similarly, there will be 2 diagonal edges. And that will be giving us 2, and that will be plus k e square, and the distance between two is our a square plus b square. So total energy will be the summation of all these three. If you can say the total energy let us call this as U1 will be equal to the summation of these two, and we can take these two as common. So this will become minus 2 k e square will be common. It will be 1 by a plus 1 by b plus, and second will be coming as 2 k e square square root of a square plus b square. And we are only interested in that we have to find out what will be the, whether the work done will be positive or not. We are interested in the sign. Okay. Therefore, we can say sign of U1 And one thing we can be very sure of, that a square plus b square will be always greater than a, and similarly a square plus b square will be also greater than our b. This thing is, we are very sure about it. Okay. So therefore our positive diagonal term will not be able to overcome the four attractive edge terms. So it means this negative sign is going to dominate as compared to this positive sign. We are not interested in the actual magnitude, we are only interested in the sign. Okay. So we can say that this U1 will be our negative. So from here we can say that our U1 will be our less than 0. Okay. And this will be true for all a and b up till they are greater than 0. Now we come to our this second term, or second arrangement rather. So you can say our arrangement 2, okay. And in this arrangement, so this was our A, B, C and D. Now in this case we arrange our this particles, charge particle plus, and this is minus, and this is also minus. Okay, now the same particle are along the length. Okay. Or we can simply write this as well plus E, minus E, plus E and minus E. This is the second arrangement of our charged particle. Now we are going to find out once again what will be the pair contribution about these charges. Pair contribution. And first let us consider the top and bottom edges. And obviously there are two, okay, and the distance between them is our A. Okay, so this the distance between them is our A. So we get from here will be equal to 2 plus k e square upon A. And then we come to our left and right edges. And there are two, and the distance between them is about b, so this comes as twice minus k e square upon b. Then we come to our diagonal part. Diagonal edges, and there will be also over 2, and so we get this as about twice, and diagonal will be always opposite charge, so this is minus k e square, and distance between them is our a square plus b square. Once again, total energy and that is our U2, and U2 we can easily write this as our 2k e square will be 1 by a minus 1 by b minus 1 upon a square plus b square and its square root. So this will be total energy, that is our U2. Okay, and we are supposed to find out whether the work done will be positive or not. So for positive work, we know that our U2 should be greater than 0. So you can say for positive work, our U2 should be greater than 0. Okay. And which basically means that 1 by A minus 1 by B minus 1 upon A square plus B square should be greater than 0. And for the sake of convenience, let us write that our x is equal to b upon a, and where x is positive. Therefore, we can write this equation as 1 minus, this comes as 1 upon x minus 1 upon square root of 1 plus x square should be greater than 0. And let us define this as a function f of x. Okay, and we can just approximate the sign. So we define f of x is equal to 1 minus 1 upon x minus 1 upon 1 plus x square and its square root. Okay. So this our f of x will be less than 0 for our x is approximately equal to 1. Because this negative sign is going to cancel out, and this term will be only the negative sign will be left, and this our f of x will be going towards 1 as x tends to infinity. So from here you can see that there is a single critical value which we call as x critical, for which this f of x is equal to 0. Therefore, we can say that there is a single critical value, and that value, let us call this as x critical, where our f of x is equal to 0. And numerically, we can find out that our x critical is approximately equal to 3.3. So it means that our U1 will be always negative and U2 will be positive under the condition. You can say that our U1 will be always negative for all values of a and b unless until they are positive. And our U2, that is second arrangement, will be positive if and only if the ratio of the maximum value of a and b to the minimum value of a and b is approximately greater than equal to 3. So these are the conditions for which we are going to have a positive energy associated or positive work that is associated with it. next question. So it states that two charges Q are each located at a distance d from a charge Q as shown in the figure. Okay, so this is figure A basically. Okay, and it is talking about figure A. What should be the charge Q so that the system is in equilibrium, that is, so that the force on each charge is equal to 0. And part B, same question, but now the setup is in figure B. Okay, so this is figure B, setup has changed. The three charges now Q are located at the vertices of equilateral triangle. And part C, show that the total potential energy in each of the above system is equal to 0. Okay, so this is the basic question in part A as well as part B. So let us solve for part A. And this part A, we are given that we have two charges Q and one charge is capital Q. Okay, and they are at a distance d equivalent from this charge Q. Okay. Therefore, if we draw a axis at this charge Q, so both these charges are symmetric. And therefore, by symmetry, we can say that force on this charge capital Q, they are going to balance out each other, because this small q is going to repel it to the left side, and let us suppose this is our A, this is our B, and this is C. So we are going to have this as our FC, and toward this side we are going to have our FA. The magnitude of the charges are same and the distance between the two is same. So these two are going to balance out each other. Okay. So we can also draw without any this calculation. We can say that by symmetry the force on Q from both the charges will be cancel out each other. So we can say that by symmetry force on Q from two small q cancels. Mathematically we can also prove it, because the charges are same, the distance between the two is also same, so they are going to balance out each other. And we have to find out that force on each charge is 0. Okay, we have to remember that the force on each charge should be equal to 0. So in the first charge, that is a capital Q, we have easily proved. Now we come to our this force balance on one charge, any of charge, whether A or at C. So you can say force balance on charge small q. Okay. So there will be a force on this, suppose we take charge A, then there will be force because of charge at C and force because of the charge at B. Okay. Force balance on charge A, that is our at point A. So first of all, let's find out the force due to charge at C, and at charge C is small q, and we can say that our this force is our Fc, and Fc will be equal to k q square, and the distance between the two is our 2d, this whole square. So we get this as k q square 4d square. And obviously the direction will be repulsion, okay, towards the left side. Okay, so we can say it will be repulsive. And then is our force due to charge at B. Charge at B, and at B is our capital Q. So we can say this as our FB is equal to K Q small q, and distance between the two is our d square. And here we can put this in magnitude, because we need that force on this charge at A should be equal to 0. Okay. So it means because of this, let me draw it here. So this is our charge A, and force because of charge C is Fc on the towards the left. Therefore, the force because of this Fb should be towards the right, because then only the force, net force at A will be equal to 0. Okay. So this Fb will be attractive. Okay. And it will be towards the right side. Okay. And so we can easily use the equilibrium condition. We have the equilibrium condition, and we can just equate them. We get this as our K Q capital Q upon d square is equal to K Q square upon 4d square, and this Q square, d square, K and K cancels out. Therefore, from here we get that the Q will be equal to Q by 4. Okay. And this will be attractive only when the sign of Q is negative. So this Q will be equal to minus of Q by 4. And now we come to our part B, where the charges are arranged in the triangle. And so you can just draw the triangle, and the distance between this is all are d. So these distances are d. And this is our Q, Q and Q. And this is our capital Q. And the distance is our d. Okay. And one second. Okay, we can just solve it by using, let us do not consider this d. We consider that we have this equilateral triangle, and the side length of this triangle is A. We will solve it that way. It is much more convenient to solve this. So let us remove this D, and we say that we have equilateral triangle whose side is our A. therefore this our charge Q is placed at the center of the triangle. Charge Q is placed at the center of a triangle, and the distance will be, suppose, our r, and that will be equal to a square root of 3, where a is the side length of the triangle. And this, by symmetry, we can clearly see that the force on this net charge Q will be equal to 0, and because the distances are same and the forces are going to balance out each other. Therefore, we can say that net force on Q is 0 by symmetry. There is no need to calculate it. So once again, we are only going to find out with respect to one of these charges. Let us call this our A, B and C. So let us consider the charge at A. So we can say that forces on charge at A, and charge at A is having a charge of Q. So we have our, this is our charge A, this is our charge at B, and this is our charge at C. So there will be a repulsive force because of B, and it will be in this direction, so let us call this our FP, and because of C there will be also repulsive force, that is our FC, and their resultant will be somewhere here. Let us call this as our F, and we can just extend this, and this is our charge Q. This is the basic. And so we have a repulsive force because of charges at B and C. You can say that repulsion from charges at B and C, and both are having charge Q. Therefore, we can say that each force means force because of our FP will be equal to, and it will be same because their distance is also same and the value of the charge is also same. So we can say FB is equal to our FC is equal to, suppose, our F, and that is equal to our K Q square upon A square. And sorry, let us call this as FQQ. And now we can find out the resultant, this FQQ, because of these two forces. So we can say that our FQQ, and the angle between the two, because this is a 60-degree angle, so obviously this will be also a 60. So both are having 60-degree angle and magnitude of both are same. So FQQ is nothing but the resultant of this FB as well as of FC, which are same in magnitude, and the angle between the two is our 60 degree. Okay, so we can say that angle between FC and FP is our 60 degree. So we can say the resultant FQQ will be equal to square root of 3, and that will be our k q square divided by a square. Okay, resultant of two vectors basically. Okay, and it will be acting radially downward. Okay. And now we come to the force from charge q, capital Q. Force from capital Q, and let us call this as F. Q, capital Q will be equal to K, and this comes as Q, capital Q, and we have our R square. And R we already know, so this comes as our K, Q, Q, and this is our A square root of 3 and whole square. Therefore, we get that F Q Q will be equal to, this comes as our 3 K Q Q upon A square. So this is our magnitude of the force, and we are going to keep this in a modulus. Okay, because, and we are supposed to say, or in the question it is given that the net force on this A is 0. So obviously this FQQ will be acting in the opposite direction to that of this F small qq. Okay, so it will be attractive in nature. So this was our repulsive. And this has to be attractive. And so both should be, for net force to be 0, we can say at equilibrium we can write that our F QQ is equal to F small qq. So we substitute them, we get this as 3K Q Q upon A square is equal to, and this is our square root of 3 K Q square upon A square. So this A square, K, Q and Q cancels out. Therefore from here we get that our Q is equal to Q upon square root of 3. And for attractive, this sign will be of negative. Then it will be our attractive. So we can say that Q will be equal to minus of Q upon square root of 3. Now in the B part or C part, we are supposed to find out the total potential energy of both the cases. So we are supposed to find out total potential energy So total potential energy or total electrostatic potential energy, general formula we already know, that U is equal to our summation K Qi Qj Ri Rj. So this is our general formula for our electrostatic potential energy. And let us consider the cases one by one. So we have our case A, and we have two pairs of charges. So we have one pair is our Q to Q, and distance between them is our 2d. And therefore we can say that u QQ will be equal to this will be plus k q square upon this is our 2D, and then we are having two pairs of, this was our one pair and we have two pair of this q and small q, and the distance between them is our d. Therefore we can say that our energy will be equal to UQQ, and we know that the sign is for Q is our negative sign, capital Q rather, so this comes as our twice minus K, and we also know the relationship between our Q and, so this will be QQ upon D square, and we know the relationship between this capital Q and small q. Therefore we can write that our UQQ will be equal to, this comes as minus of 2 and this is k q square upon, sorry this is not square, my mistake, this is our 4D, and here this goes by 2, so we are left with minus k q square upon 2D. So it means total energy will be summation of the two. Total energy, that is our U, will be equal to U because of, and this is our second case, and we get this as a plus k q square upon 2D minus k q square upon 2D. These two cancels out, therefore first case we are having that total energy is equal to 0. Now we come to the part B, case B rather. And case B, once again we are going to form the pairs, and we can see 3 pairs of small QQ. So we have 3 pairs of QQ and each is at a distance of our A. Therefore the energy is our UQQ is equal to plus 3k q square upon A, and there are 3 pairs of capital Q and small q, and their distance between them is our A square root of 3. So we get this energy will be equal to, this will be 3 minus k q square upon A. Okay, we can directly you can say put the relationship. So total energy in this case that is our U will be equal to UQQ plus U capital Q and small q, which is our plus 3k q square upon A minus 3k q square upon A. Once again these two cancel out, therefore we get that total energy is equal to 0. So in both cases we get that total energy is equal to 0 in the both systems. So these were the questions, 4 questions from our electrostatic. And so thank you.